So when we finished up class on Wednesday, I believe it was, we had analyzed a rather large circuit and we had determined what the value of the capacitor voltage was as a function of time. Okay. So we have two paths here that we can take. We can either circle back around and figure out what our inductor current was, because that is our other quantity of interest that we wanted to talk about, effectively just reapplying the rules to the quantities that we determined, or we can verify our solution using LT spikes. We're going to wind up verifying our solution using LT spikes either way. So the question is, do you want to do the inductor current first and do our analysis of both quantities with LT spikes, or do you want to make sure we were right with this, figure out what the inductor current is, and then make sure that we were right as well? So do you want to do LT spice analysis, LT spice, or analysis and then long LT spice? Long LT spice. Okay. So let's circle back around here to the beginning. We're not actually going to redo any of this analysis whatsoever. I just want to make sure that we are all on the same page as to where I started this problem. Here we go. Okay. So we did, I would say, a large amount of work to figure out what this quantity VC as a function of time is. Okay. So the first thing that we had to do was to determine what type of circuit this was. And we concluded that this is behaving like a series RLC circuit, because during the transient condition, with this voltage source turned off, we see energy transfer from our capacitor flowing through our inductor, and effectively it's just these three elements right here forming a loop, telling us how our transient condition is behaving. Okay. We then used our table to determine alpha and omega naught for this circuit, and concluded that it was a underdamped series RLC circuit. We analyzed the circuit at t is equal to 0 minus, paying attention to the value for the capacitor voltage and the inductor current at 0 minus. We then analyze the circuit at t is equal to 0 plus, where we determined the capacitor voltage, the capacitor current, the inductor voltage, and the inductor voltage and the inductor current. And then we analyze the circuit at t is equal to infinity, where we only paid attention to the capacitor voltage and the inductor current, because those are our two quantities of interest. Okay. So to recap, at t is equal to 0 plus, we need to know both pieces of information about both of our energy storage elements. Okay. We need to know the voltage across the capacitor, the current flowing through the capacitor, the voltage drop across the inductor, and the current flowing through the inductor. And the reason that we need both pieces of information is because we're using a derivative-based relationship to write our system of equations, which tells us what our coefficients are. I'm distracted by your shirt because I have the exact same shirt. Sorry. So we can use all that information that we collected to figure out exactly how I of t is behaving as well, because we took note of it. Okay. So scrolling all the way down here to a new page, let's start our inductor current analysis. Since we have an underdamped system, we know that I of t is of the form B1, where this B1 is an entirely new coefficient. I can call it B3 if you want me to, so that we recognize that it's not the same B1 as we saw for our capacitor voltage. I think that'll probably be easier. So let's call it B3 cosine omega dt plus B4 sine omega dt e to the minus alpha t plus I at infinity. We know this is how the inductor current behaves because we know that we have an underdamped system, all right? Omega d is the exact same omega d that we solved for on Wednesday. That is not going to change, okay? Nor is alpha, nor is omega naught. The only things that are going to change are our coefficients. So I at 0 plus is then simply B3 plus I at infinity. Effectively, we get practically the exact same expression as we did for our capacitor voltage, except that now we're going to use the value of the inductor current at 0 plus and the inductor current at infinity to figure out what that coefficient B3 is. So what was the inductor current at 0 plus? 0.4 amps. And what was the inductor current at t is equal to infinity? 2 amps. All right, so we can simply solve this one unknown equation, and we would find that B3 is 0.4 minus 2, which is negative 1.6 amperes, if my mental math is correct. And we know our coefficient B3. All right. Now we're going to use our derivative-based relationship, which is the inductor voltage, to determine the value of B4. So the voltage drop across an inductor, VL of T, is L di by dt, which is going to look like L times whatever the table tells me the derivative looks like, which is the purpose of making the table. So for an underdamped system, the derivative of our quantity of interest is going to be omega d B2 minus alpha B1 cosine omega dt minus omega d B1 plus alpha B2 sine omega dt, that whole quantity e to the minus alpha t. And at t is equal to 0, this reduces to L times omega d B2 minus alpha B1. Where the only thing we don't know, oh, sorry, this should be 4, 3, let me fix that because we're using different things. That's I mixed myself up there, so I apologize. Since we're using B3 and B4 to represent our coefficients, I'm just making that consistent. My mistake. So everywhere I had a 1, I put a 3. Everywhere I had a 2, I put a 4. Yes.
Yeah.
Okay. All right. So let's go back and revisit that. So I'm being told that the current flowing through the inductor at t is equal to 0 plus was 1.6 amps. Okay. So 1.6 minus 2 gives us B3 is equal to negative 0.4 amps. So that should be the correct value. Okay. All right. Thank you for letting us know that, because when we simulated it, we would have been wildly incorrect and it would have been hunting for where the mistake was. So I'm glad we found it early. All right. So I'm just going to do simple algebraic manipulation of this guy here. So VL at 0 plus divided by L plus alpha B3. And then I'm going to divide. So that would be equal to omega D times B4. So I'm just going to divide by omega D. And if my algebraic manipulation here is correct, then this is what our coefficient B4 should be. So what was VL at 0 plus? I believe it was 0. Okay, 0 volts divided by omega D times L, which obviously is just going to contribute 0, so I'm not even going to bother with those things. All right, what was alpha? 1/2. Is that correct? Alpha is 1/2. B3 is negative 0.4 amps. And then omega D was also 1/2, right? Okay. Obviously, these 1/2s cancel each other out, and B4 is just negative 0.4. Yes. So B3 and B4 have the same coefficient. From this, our inductor current, I of t, is negative 0.4 cosine 1/2 t minus 0.4 sine 1/2 t e to the negative 1/2 t plus 2 amperes. Where I've just plugged in B3, B4, alpha, omega D, and I at infinity into our expression. Okay. So, time to simulate this and see if we made any mistakes. So, while I'm getting everything set up here, finding my mouse, etc., you guys should be opening up LT Spice and all that kind of good stuff and getting ready to ostensibly follow along with me. But if you just want to watch me do it and then look at the video later, that's perfectly reasonable as well. So what I'm going to do here is I am just going to set my schematic diagram to what this circuit looks like at t is equal to 0 plus, okay? Where I'm going to leave my inductor as an inductor, and I'm going to leave my capacitor as a capacitor, okay? So at t is equal to 0 plus, I have a voltage source. Yes, so I'm just going to leave it as an open circuit. And the reason why I draw my circuits this way is because setting up switches in LT Spice can be a bit of a pain in the butt. And I really only care about what's happening after t, t is equal to 0 plus and beyond anyway. That's the actual transient condition. So to make my life more easy, I just look at it at t is equal to 0 plus to move on. All right, so we have our 12-volt source. We have a 2 ohm resistor up here. I have my 6 ohm resistor. Honestly, I don't even need to really include this portion of the circuit because it's not contributing anything during the transient condition, but I'm just going to have it here because might as well. All right, I'm over at the right-hand side of the circuit. I'm going to have a 2 amp source. Direction up. Four ohm resistor. Let me wire these guys up. I'm about to drop in my 2 Henry inductor and 2 ohm resistor. So my inductor is going to go up here. My resistor is going to go down here. This guy has a value of 2 ohms. This guy had a value of 4 ohms. And then lastly, on the right-hand side, I believe I just need my capacitor. Is that correct? It's not that switches aren't in LT Spice, it's that it's hard to make them depend on a time in LT Spice. So I choose to do this a different way. Responding to something in chat. My capacitor is a 1 farad capacitor. All right, so is this what my circuit looks like with the switch open? So that we're during the transient condition, yay or nay? So we're not looking, so that's a fantastic question. Okay, so our simulation is not going to be just for t, the moment in time t is equal to 0 plus. It's going to be for all points in time t is equal to 0 plus and beyond, which is why we can't model our inductor as just a current source, because we're including points in time where it isn't behaving like a current source. So what we're going to do is we're going to use initial conditions to force our inductor to behave like a current source at that one instant. And we're going to use an initial condition to force our capacitor to behave like a voltage source at that one instant. And then we're going to let the signals decay as they need to. Okay. So because we're using LT Spice, we have to use a ground terminal, right? I always, always, always choose my ground node to be the negative polarity terminal of my capacitor, okay? Which in this case is simply the bottom node. Now what I am going to do, and this is just a bookkeeping kind of thing, you don't have to do it at all, but I'm going to call the positive polarity terminal of my capacitor VC. And the reason why I do that is because when I write my initial condition, effectively I'm telling it what the voltage is at, the voltage drop across the capacitor is the voltage at this node, which has a nice neat label that I set so I don't have to go hunting for it, minus the voltage drop at this node, which is inherently 0. So it's just making my expression more simple so that there's less opportunities for me to make a mistake there, okay? So to set up my initial conditions, I type .ic. I don't think it has to be capitalized, but I'm in the habit of capitalizing it, so I'm doing that. The voltage V at node VC is equal to whatever value the capacitor voltage was at t is equal to 0 plus, which was what?
It was 0. It was 0. I think capacitor would be 3.2 volts.
3.2 volts. Okay, so I'm just going to put this as 3.2. Now I can do an entirely different SPICE directive, or I can type Control M and it'll give me a second line, and I can include the initial condition on the inductor current in the same code. So I'm just going to do that bit. So Control M gets me to the second line, .ic, and then the current through inductor L1. So what was the inductor current at t is equal to 0 plus? 0.6? 1.6, thank you. Those are my initial conditions. All right, and now, yes.
Do you have that space between those equal signs?
No.
Okay.
At least not to my knowledge. And now, because I'm doing a transient analysis so that I can see how these signals behave as a function of time, I need to choose a stop time, okay? So alpha is 1/2, okay? Alpha is effectively telling me, it's playing the role of a time constant here, effectively. So that in one time constant for it to decay to a value e to the -1, that would take 2 seconds. So I'm going to arbitrarily start here with a 10-second simulation, roughly 5 times alpha to the -1 power, just to give me a ballpark of where to start. Got a question? We should see some ringing, yes. Okay.
I'm sorry, Dr. Hartman. How did you say it?
Alpha to the -1 power times 5.
Thank you.
Yep, just because alpha is telling me how this thing, the rate at which this thing decays. So, all right, so let's see what happens when I run the simulation. I have to tell it what to look for. So for the sake of argument here, let's just look at the capacitor voltage. All right, so the question that we have here is, did this actually settle to its final value or not first? Okay, are we looking at the whole picture? So what I'm going to do is I'm just going to change my transient condition from 10 to 20. We're just going to look at it a little longer and just make sure it stabilizes. Okay. So we can see that after a little bit past 10 seconds, it's pretty constant at whatever this value is. So 20 seconds seems like a reasonable time to run our simulation. Really, 12 seconds would get the job done. On your homeworks or anything like that, I just want to make sure that, you know, it's settled, but I don't want it to be settled for so long that we can't really see what it's doing. And so what I mean by that is if we looked at this for 1,000 seconds or something, the part we're interested in is this little bit right here, and the rest of this is just a DC value. It provides no information whatsoever. So typically speaking, we are going to have to play around with the duration of our analysis to get a good picture of the event. Okay, so 20 seconds was a little too long, 10 seconds was a little too short, so I'm going to split the difference, call it 15, and that seems reasonable to me. Again, we could make it as short as 12 or so and still have a reasonably good picture. Okay. So now we come to the part where we check our work. All I'm going to do is I'm going to right click and add a trace. Okay. And instead of selecting any of these signals that LT Spice simulated, I'm going to type in the result we got. So what was the mathematical expression for VC of T?
Negative 0.8
All right, negative 0.8.
cosine to the 1/2. Cosine 1/2.
Okay, so cosine 0.5 times time.
That multiplied by e to the power of the negative 1/2.
Okay, so times EXP negative 0.5 times time
Plus 4.
plus 4. Okay, I've intentionally made a mistake here. Okay, now it doesn't look like I did. I typed in literally what you told me, but I can practically guarantee that we're not going to get the right result. And we don't. So let's talk about why there's an issue. So I'm actually a little bit confused because this doesn't appear to be settling to exactly 4 volts. It looks like it's settling to 3.96. So sorry, that's another thing. Okay, so two things to unpack here. Great, I'm actually glad that I made this mistake now. Okay, so I was trying to compare these graphs. Now, obviously, they're not of the same shape. So that's definitely a problem. That is indicative of problem 1. So let's address that first. 0.5 is the radians per second. It's the angular frequency. LT Spice does everything in degrees, so we need to include a conversion factor here, only for our omega d term, okay? So I'm going to fix that by just right-clicking the mathematical expression, and I'm just going to tuck in a thing that says 180 divided by pi, where pi is just literally pi. And press OK. And it's telling me a syntax error because I forgot to put a multiplication sign. Now, I believe that's going to fix things, okay? But another thing that tipped me off that something was a little wonky here, or that I was alarmed about, was the fact that it didn't settle to what looked like the same thing, right? The DC part should be the same because that's after the transient was decayed. Well, why I'm less concerned about that right now is because the scale on the left-hand side of my graph, which is the scale that's being used for my simulation, is not the same as the scale on the right-hand side of the graph, which is the one that's corresponding to my mathematical expression. So to get a true one-to-one look at these things, I have to make sure that the scale on the right-hand side matches the scale on the left-hand side. LT Spice will automatically adjust it with this new function. So I'm going to press OK, and my green curve disappeared, which means my blue curve has completely overlapped it, and we have perfectly matched our signals. So our analysis was correct. So just to reiterate, whenever we are going to use LT Spice to compare signals, we need to make sure that the scale on the right-hand side and the scale on the left-hand side are literally identical. Now, the tick marks don't matter, but we need the same bounds. 4.14 needs to be on top, 3.15 needs to be on bottom. All of this other stuff doesn't particularly matter, but if we are not looking at it over the same span of voltage or current ranges, then we're not really comparing the signals. Another thing, I'll get to you in just a second, Dylan, is that anytime we are dealing with an angular frequency term, we have to put in a conversion factor of 180 over pi to convert it to effectively a linear frequency in degrees. And it's still an angular frequency, but it's expressed in degrees as opposed to radians, because that's the angle unit that LT Spice uses. Yes, sir.
This spice have an actual cosine function, or do I just have to change?
You have to change the phase angle.
Where would I change?
Okay,
Like if I was gonna assign these little wave functions, they have like a phi, theta, delay.
phi,
It need to be 90, correct?
negative 90. Sine is,
Thank you.
sine of minus 90 is cosine, right? We'll get to that again in a couple of weeks. So that might be, it might be positive 90, whatever. I can never remember if it's plus or minus sign. But anyway, yeah, so this is the term that you would change to force a sine function to look like a cosine function. This is the angular, the phase angle bit right here. Theta here has units of 1 over s, but I'm honestly not sure what s, I believe it's seconds, because the delay time is absolutely measured in seconds. I'm not sure what this parameter actually does. But if you want to change the phase angle, it's definitely phi. Okay, so let me cancel this out. All right. So now what we're going to do is we're going to look at the inductor current. Okay. On your homework problems, if you happen to have looked at them, I usually ask you to tell me what's happening with two quantities. Okay. So what I'm going to do now is I'm going to right click and I'm going to add a plot pane so that now I'm able to put two separate graphs into LT Spice. If I click into the area of the empty plot plane, and now I come down here to my simulation and I get my current probe over my inductor, I've now plotted my inductor current. And then I can right click into here and type in my mathematical expression for my inductor current. So if I'm not mistaken, this was negative 0.4 times the cosine of 0.5 times 180 over pi times time minus 0.4 times the sine of 0.5 times 180 over pi times time, close parentheses, multiplied by exp negative 0.5 times time plus 2 and that new curve, which was the mathematical expression I just typed in, completely overlaid the simulation results, meaning that our analysis and determination of the inductor current was also correct. Connor, did you have a question?
No, sir.
Okay.
Thank you.
All right.
Sorry.
Yes, no, not a problem at all. So to recap here, to add our mathematical function, we add trace and literally just type in the mathematical expression. To add the second plot plane, we just right click on the graph and tell it to add a plot plane. Then we do the same thing.
Does LT Spice, it needs that asterisk to multiply?
Yes, it will not implicitly multiply. That is correct. It's not as good at math as MathCAD is, which MathCAD, if you don't implicitly multiply, sometimes treats things inside parentheses as a function of the other thing acting on it. So it's always a good idea to implicitly multiply there as well, actually. All right, how do you guys feel about doing the simulation and all that kind of good stuff? All right, so let's take, we still have, this class ends at 12:15. Okay, so we got a little over half an hour. Let's work another problem that isn't quite as involved. My hope here is to find one that isn't underdamped as well. let's look at this guy. It doesn't seem particularly difficult. And if I have to change the value of something to make it not underdamped so that we're not doing literally the exact same analysis, then I will. Okay, so let's say that we have this circuit. Where we have an 8-volt source. Let's say that we have a switch that's opening at t is equal to 0. Actually, I take that back. We need to have it closing. Here we have a 12/5 Henry inductor. Here we have a 2 ohm resistor. And here we have a 1/12 of a farad capacitor. Let me put it over here. And what I'm going to look for in this case is the voltage drop across my capacitor. And I'm just going to call that V of t in this case. And the current through my resistor. Okay. Now, the reason that I'm choosing to look at the current through my resistor is because I want to talk to you guys briefly about this. Okay. So when we analyzed the last problem for the capacitor voltage, we used the capacitor voltage equation, the response equation, and then we used the derivative based relationship for the capacitor current, right? When we did our work for the inductor current, we first set up our system of equations involved the inductor current response equation itself, and then the derivative based relationship, which had to do with the inductor voltage. So we always had the response equation and then the derivative of the response equation. The problem here is that for a resistor, there is no derivative based response equation, which means we can't actually use this method to solve for the resistor current directly, okay, or resistor voltage. Another way to think about that is the resistor isn't an energy storage element, which means our initial conditions on it don't actually mean anything because it can change values abruptly, okay? So the resistor is an unreliable quantity to be able to figure out how the system behaves as a whole. But in this case, with the resistor directly in parallel with our capacitor, if we know what the capacitor voltage is, the resistor current is just the capacitor voltage divided by the resistor value. If we wanted to know what the resistor voltage was, well, it's literally the same thing as the capacitor voltage, right? So we can get the resistor voltage and current always by looking at some combination of the capacitor voltage or the inductor current, but we can never calculate it directly using this method, okay? All right, so during the transient condition, looking at a dead network, what kind of circuit is this? If I need to draw it, I'll happily do so, but I feel like we can look at it and figure it out.
Just a shot through that resistor.
So during the transient condition, this switch is closed. So it's a short circuit. With a dead network, the 8-volt source is also a short circuit, which means our inductor is in parallel with our resistor, which is in parallel with our capacitor. So it's a parallel RLC network. Okay. So for a parallel RLC network, what is alpha equal to? Look at your table. 1 over twice RC. Thank you. That's 1 over 2 times 2 ohms times 1/12 of a farad. So that's 1 over 4/12. So 12 over 4 is 3 nepers per second. And omega naught is the square root of 1 over LC. So that's 12/5 of a Henry times 1/12 of a farad. So we would have the square root of 5, I believe. I'm going to double check that since I did that in my head. Square root of 5 radians per second, which is 2.236 and some change radians per second. So alpha is greater than omega naught, which means that this circuit is an example of a overdamped. Right. Anytime alpha is greater than omega, we have an overdamped circuit. All right. Now we're going to analyze this circuit at t is equal to 0 minus. The switch is open at t is equal to 0 minus. So I very strongly believe that everything is 0 because it's not connected to anything to make it not 0. So by inspection, V 0 minus is equal to 0 volts. IL of 0 minus, which I guess we technically need to assign a direction for this as well. So what I mean by that is how the inductor behaved at 0 minus is going to influence our analysis at t is equal to 0 plus. Right now, we haven't indicated that we're keeping track of anything having to do with the inductor because we aren't specifically asked to, but we absolutely need to because it influences the behavior at 0 plus, okay? So pick a direction, left or right?
Right.
Right, okay? Here's IL, 0 minus. We know that it's 0 amps. And IR, for what it's worth, is also 0. We don't actually have to keep track of any of the resistor quantities whatsoever because we're just going to use other things to get it at the end. But if you want to, or sometimes I will ask you to do it for, I don't know, whatever reason. So we can keep track of it, just for the sake of doing it, let's say, okay? All right, so that's our analysis at t is equal to 0 minus, where we didn't really have to do any analysis whatsoever. Again, our excitation source was not connected, so the answer to everything has to be 0. Now we'll analyze at t is equal to 0 plus. So at t is equal to 0 plus, we have our 8-volt source. Our switch is a short circuit. but our inductor is an open circuit. Here's VC at 0 plus. Actually, that's not correct. It should be a short circuit. It's going to be 0 either way, but it should be a short circuit. Yes. All right. Here is our capacitor current at 0 plus, which we need to pay attention to. And just for the sake of argument, here's IR at 0 plus. What are the values for these two quantities? Have to be 0 again. Some number. IC at 0 plus is also 0 ohms. Okay. How do we feel about this analysis? Pretty straightforward. Lastly, we analyze the circuit at t is equal to infinity. At t is equal to infinity, we have DC steady state. So our switch is closed. Our inductor looks like a short circuit. Here's our 2 ohm resistor. Our capacitor looks like an open circuit. Here's VC at infinity. And then here's IR at infinity. What are the values here? Absolutely right. So V at infinity is 8 volts. IR at infinity is obviously 4 amps. Right.
So the inductor is a short circuit, not a, I'm sorry,
Yes, so at t is equal to infinity, we are at DC steady state. So we replace our inductor with its DC steady state equivalent, which is short circuit. We replace our capacitor with its DC steady state equivalent, which is an open circuit. All right. Now we are to the point where we use our table and all that kind of good stuff, right? We've analyzed the circuit at t is equal to 0, minus, t is equal to 0 plus, and t is equal to infinity. We know that it is a overdamped parallel RLC circuit. So we need to calculate S1 and S2 because it's an overdamped system. So let's go ahead and do that bit first. Okay. So S1 is negative alpha plus the square root of alpha squared minus omega naught squared. So that's -3 plus the square root of 9 minus 5, -1. S2 is negative alpha minus the square root of alpha squared minus omega naught squared. -5, and both of these have units of just per second. Anybody else calculate those and get those numbers? All right, so we have S1 and S2. We are going to look for our capacitor voltage. So because it's a overdamped circuit, our capacitor voltage will be of the form A1 e to the S1t plus A2 e to the S2t plus V at infinity. Directly from the table. At t is equal to 0, we have V of 0 is equal to A1 plus A2 plus V of infinity, or A1 plus A2 is equal to V of 0, which is 0, minus V of infinity, which was 8. So A1 plus A2 is negative 8 volts. Everybody okay with that? Our inductor current, IC of T, is C dV by dt, which is going to be C times S1A1 e to the S1t plus S2A2 e to the S2t at 0. This looks like C times S1A1 plus S2A2. Right? So C is 1/12. So let's see. IC at 0 was 0. So we have 0 amps is equal to 1/12 of a farad times S1, which was -1 times A1 plus S2, which was -5 times A2. So that means that -1/12 A1 minus 5/12 A2 is equal to 0. We have one equation, two equations, and we can solve that system. So let's do it. So coefficient for A1 on our first equation is 1. Coefficient for A2 in our first equation, constant term is -8. Coefficient for A1 is -1/12. Coefficient for A2 is -5/12. Constant term is 0. Solving, I get A1 is -10 volts. A2 is +2 volts. And from this, our capacitor voltage, VC of T, is A1, so -10 e to the S1, so that's -1 T, plus A2, so +2 e to the S2, so that's going to be -5 T, plus V at infinity, our resistor current then is simply VC of T over 2 ohms, or -5 e to the -t plus e to the -5t plus 4 amps. And we will simulate these results to make sure that we did our analysis correctly, and then we'll call it a day. Waiting for you guys to stop what appears to be writing things down to let me know when we can switch over to LT Spice. We good, Catherine? All right. So I'm going to delete this jibber jabber, delete this, new thing. So we've just got our voltage source. Oh, I shouldn't have put a volt there. A1 was -10, A2 was 2. And then I have my inductor here, which was 12/5. LT Spice doesn't like fractions, so 12/5 would be 2.4. All right, so my resistor goes here, and it was a 2 ohm resistor. My capacitor goes here, and it was 1/12. 1/12 is 0.08, and then a lot of threes. I'm going to put ground at the bottom because that's where the negative polarity terminal of my capacitor was. I'm going to label the positive polarity terminal as VC again. And I missed. There we go. I'm going to put in my initial conditions. So that's dot IC, the voltage at node VC equal to 0. Control M, dot IC, not a dot. The current through inductor L1, 0. Let's start with 5 seconds here and just see what falls out. So we're definitely getting really close to 8 volts at t is equal to 5 seconds. Let's just look at 8 seconds so that it's actually just settled for a bit. Yeah, okay. That seems good. It's been settled for about 2 seconds. We're going to add our trace. So that's going to look like -10 times EXP negative time plus 2 times EXP -5 times time plus 8. And they match. Obviously, if the voltage matches the current, the resistor current's going to match because it's literally just this divided by a factor of 2. Right, so I'm not going to bother actually simulating that one and showing you. Okay, so we've worked an example of a series RLC circuit and a parallel RLC circuit at this point. I've shown you how to simulate the results of our analytical solution and show that they match the simulation. I've talked about some potential pitfalls to consider. If you're ever strongly feeling that your results are correct and the simulation it isn't matching, again, look to make sure that your axes are the same on both sides of the graph. And in the event of an underdamped response problem, make sure that you have remembered to include the conversion factor of 180 over pi every time you have the term omega d. So I think that is enough out of me for today. What we are going to do on Monday and Tuesday is we are going to look at general RLC circuits, right? So not everything fits neatly into a bin that is either a series RLC circuit or a parallel RLC circuit. So we are going to take our knowledge of these special cases to develop a rule set to handle general RLC. That does unfortunately involve a little bit of calculus.